for those, just for you to know, to accept the recording, and there will be a round of questions at the end. Yeah, so thanks very much.
Thank you all for being here, and thanks Nacho for the introduction and the invitation. So today I'd like to give an introduction to what we know as cosmic shear, which is the lensing, gravitational lensing by large scale structure, which tells us a lot about dark matter and dark energy. And here on the title slide, I have this animated GIF, which was made by one of the Dark Energy Survey members, Niall Jeffrey. And it's a map of the lensing signal over the Dark Energy Survey footprint. And then, of course, in the background is data from the Gaia collaboration. Okay, so the things I'd like to talk about today. So the first thing I'll start out with is just a very brief context and background, how this gravitational lensing compares to some of the other observations that we make that constrain dark matter and dark energy. And then I'd really like to focus mostly on this second bullet point. So this is actually, these items will take up most of the time. And that includes going into some background for the formalism for weak gravitational lensing, talk about the measurements that we make, and then link that to the theory or the models. And then the last 3 points here are going through a brief history of these measurements, and also just going over a couple of recent Dark Energy Survey results that have made it to the archive already, and then talk briefly about the path forward with these future experiments that will be measuring this cosmic shear. All right, so here are some images that you've probably seen many times before. So the idea here is that we have a very expansive view now of the universe from very early times with the Planck satellite and other experiments at very high redshift, so when the universe was very young, and emitted these photons, which we now detect as microwave, as the microwave background, the CMB. And then from that early time, and you can also see it in these snapshots from the illustrious dark matter simulation, going from higher redshift to lower redshift, where as time goes on and redshift goes to 0, which is today, the universe has been expanding, but also these structures have been coalescing through gravity and forming what we see as this very filamentary structures, where there's lots of very high density peaks and also voids with basically very, very little in there. And so we have this picture now where there are these competing forces. There's the dark matter and also ordinary matter, but the ordinary matter is really only a small % of the total matter. And this matter has the gravitational attraction, but then there's something causing the accelerated expansion of the universe. And so we're calling it dark energy, but there's a lot that we don't know about these things. And so that's, I think, what brings most of us to this sort of study. Okay, so far we've built up a range of observations, which seem like each piece of this seems like a different clue to potentially an overarching model, which we call lambda CDM. So that's the lambda for dark energy and then cold dark matter. And we have these different observations that are sensitive to different aspects of the properties of the universe. Some are telling us specifically about the geometry. So for example, distances and expansion of space. So I'm calling that geometry here. And that includes things like supernovae, baryon acoustic oscillations, and the CMB angular power spectrum. And then there are several observations that tell us a little bit about geometry, but maybe a lot more about structure growth. So how these mass structures evolve over time. And gravitational lensing is the one that I will focus on today, but also the counts of galaxy clusters contain some information on that, as well as redshift space distortions. And here's a plot from 10 years ago now, from the Supernova Cosmology project, which on the x-axis has the matter density omega matter, and then on the y-axis, the dark energy density omega lambda. And some of these are just the top probes here that give information on geometry. But you can see that they have different orientations in this particular plot. And so they each contain different pieces of information and together are very complementary. And if we look at the situation today, here's a plot from one of the dark energy survey results. And now this is a couple years old, but it's combining now the weak gravitational lensing plus large scale structure measurements plus supernovae and photometric BAO. And various of you in the audience, I think, have worked on different aspects of this. And that is all coming from within a single photometric survey, DES. And those measurements are shown as these gray contours here. And just to point out that this is now a very small subset of this plot from 10 years ago. And so we're kind of starting to narrow in on these parameters. So today I'll focus mostly on weak gravitational lensing, and going way back, it's this phenomenon where the light from distant galaxies, as shown here, and as the photons travel to us, as they pass by massive structures, the path of the light gets deflected by the mass or the gravitational potential of these foreground structures. And so what we might see on a two-dimensional projection, so usually there's something with light actually indicating the positions of these foreground structures, but here let's say that it's mostly dark matter. And so they're indicated by these circles. And then the light that we receive when projected appears to us as these galaxies here, which have been stretched with respect to the positions of these, what we call foreground lenses, compared to the original shapes, where in this schematic, they started out as being relatively round. Okay, so the things that matter in this analysis, there's two main properties that we measure to do any gravitational lensing analysis. One of these ingredients is the source galaxy shapes. And then the other ingredient is the redshift distribution, telling us about the geometry of the scenario. Okay, so now if we have a more simplified schematic on the left, and this is coming from a review article by Bartleman and Schneider, which has quite a lot of the information that I've left out of this talk. So I'm taking kind of a top level look at some of the equations, but if you want to see how they're actually derived, this is a great resource. So in this picture now, the observer is at the bottom, and the thing that's doing the lensing with the mass is in this lens plane. And then the source galaxy is located in this source plane. And here we have these different angles or vectors, which represent, so beta is an unlensed source position. Theta is the observed source position. And then there are two ways of expressing the deflection angle, which is the angle, so this alpha hat is the deflection angle that causes the observed source position theta, the observed source position to be at angle theta from the unlensed source position. And then this alpha without the hat is a reduced deflection angle. And alpha hat and alpha are related here. And importantly, there are this ratio of angular diameter distances. So d sub s is the distance to the source, so the thing that's getting lensed, and then ds is the distance between the lens and the source. And for a point mass lens, this is 4 gm over the psi, and that psi is a two-dimensional vector in the plane, like a radius in the plane of the lens, and then also a factor of speed of light squared. And the thing to keep in mind here is that all the angles are very small, and all the distances are angular diameter distances. And here is a relationship called the lens equation, which relates these three quantities: the unlensed source position, the observed source position, and then the reduced deflection angle. And there are some approximations that we make here for this weak lensing regime. Before, in the previous slide, you saw what the deflection angle was for a point mass. Now we're going to use the Born approximation to sum these deflection angles from a bunch of point masses. So if you think about integrating over some unit mass dm, we're going to sum that over the undeflected path. And the other approximation is what we call the thin lens approximation, which is where we are assuming that you get a really strong deflection right in the plane of the lens, but it very quickly drops off if you're not in the plane of the lens. And so you can assume that that deflection is really just happening in a single plane. And then this is the more general case where you have the mass as a function of this radius psi. And then the mass is can also be given as the integral over the two-dimensional mass surface, the surface mass density over that radius. Okay, there are some interesting quantities to define. So one is the dimensionless surface mass density, which we denote as kappa. And theta here, again, is the vector indicating the observed source position. And we're going to define this kappa as a ratio of two surface mass densities. So that makes it dimensionless. The one on the top is the surface mass density at the observed source position with a factor of the angular diameter distance to the lens. And then there's this quantity on the denominator, which we know as the critical surface mass density. And it's a combination of the angular diameter distances and some physical constants. And this is an interesting quantity because it sets a scale between weak and strong. So if kappa is greater than 1, so if the surface mass density is larger than the critical surface mass density, that's what we're thinking of as a strong lensing regime. And you can, in some cases, get multiple images. And so you can see the effect of the gravitational lensing by eye. So many of you probably have seen Hubble Space Telescope images where you have a huge galaxy cluster, and in the background you have these huge arcs and multiple images of background galaxies. So that's an example of strong lensing. But in the cases that I'm talking about in this talk, and the more ubiquitous case in the universe is that we have a weak lensing effect, where the critical surface mass density is actually larger than any particular surface mass density of a lens. And also to note here that the deflection angle can be written as a gradient of the deflection potential. And then this is what I'm denoting as psi. And this is a two-dimensional analog of the Newtonian gravitational potential. So this also satisfies the Poisson equation. And we also often use this Jacobian matrix, which tells us how to transform between unlensed and lensed coordinates. So this Jacobian, I'll denote as capital A sub ij. And that's given by these equations here. So it's kind of relating again the unlensed position and the lensed position, and telling us how to how that also relates to the lensing potential. This top thing can be rewritten, broken up into two parts. The first term is in terms of kappa, and this is a convergence term, and this serves to magnify the image. This magnification conserves surface brightness, but makes the size, it could make the size bigger or smaller. And then there's a second term here with a gamma. So we're going to use gamma a lot in here. So that refers to the lensing shear. And this term stretches the image tangentially with respect to the position of the lens. And in this matrix, this phi is the angle between alpha and the x-axis. And rewritten again, this lensing Jacobian can be written like this. And we're encoding all of the shear information into a complex number, which is, there's a magnitude, and then there's a factor e to the 2i phi. And this factor of 2 indicates that it's invariant under rotations of 180 degrees, which we'll see in this diagram to the right. And we often refer to the real part as gamma 1, and then the imaginary part as gamma 2. Before we go to the other two parts here, if we look at this diagram on the right, so this was made by a grad school classmate of mine, Jim Bosch. You can see what the impact is on something that was originally circular. So the original source is shown as this green shaded circle in each of these cases. So the green is the same in all of these. That's the original source image. And it shows you what happens if you have either positive or negative values of kappa or gamma 1 and gamma 2. And you can see if kappa is less than 0, then it serves to shrink the size of the image. And then if it's greater than 0, it makes the size larger. And then these two gamma components stretch it in different orientations. So this one is sort of vertical, horizontal, and then this imaginary part is rotated by 45 degrees. And then a comment here is that we actually observe the reduced shear. And so in most large-scale structure analyses, we don't actually correct for this kappa term. We assume that it's really, really small. So that this reduced shear is basically equal to gamma. And we can talk later about whether that's a good approximation or not. But so far, it seems to be a reasonable thing to do. All right, so here let's think about what we have to do to actually measure this signal. So if we look at this top equation where the observed ellipticity of the galaxy is equal to the intrinsic shape, the intrinsic ellipticity, plus some applied gravitational lensing shear. You can imagine that just from this top equation, we don't know what this first term is. We don't know what the shape of the galaxy was originally. So we can't solve for this G, just given one background galaxy. But if we look at measurements over lots of galaxies in the sky, and start to take averages, then if we take the mean of all of these quantities over a large number of galaxies, we can say that the mean observed ellipticity is equal to the mean intrinsic ellipticity plus the mean lensing shear that was applied. And then we're going to assume that the mean intrinsic ellipticity is 0. And that's simply saying that as you make, without gravitational lensing in the picture, just galaxy shapes across the sky are randomly oriented. And so on average, this distribution cancels out to 0. And there are cases where this is maybe not a good assumption. Some of you might have heard or perhaps even studied the intrinsic alignment of galaxies, where galaxies nearby each other are physically aligned due to local gravitational tidal fields. And then we can also talk about that later. And then if we look at the variance or the standard deviation of these quantities, so then taking the standard deviations of these three items, the observed ellipticity, this sigma is dominated by the first term because the intrinsic ellipticity distribution has a width to it. We don't have galaxies that are all basically drawn from the same ellipticity, like they're not all circles. And the second term is very small. So you can kind of see from here, in order to beat down the impact of this intrinsic ellipticity, you have to make measurements of many, many galaxies. Okay, and then having said that, we can also look at this figure on the right, where if we first focus on the left column, that's where you don't have any lensing. So G is 0 in that case. So without shape noise, they're all basically these circular points. But with shape noise, that means that these shapes are all being drawn from some distribution of ellipticities that has some width. And so you can see in this bottom left that you get just more of a variety of different ellipticities to start out with. Now on the right-hand side, it's a very exaggerated view. It's very rare that you find a lens that distorts the background galaxies in such a strong manner. But here we've put a very massive, say, galaxy cluster in the center of this image. And that serves to stretch out the shapes of the background images. In this top case, this is what it looks like without the background images having any variation in the ellipticities. And then the bottom right this is closer to the reality. And so you can see that it's a little bit hard to see. We've exaggerated it, so it's pretty easy to see the effect, but maybe if you're starting to go out to the edges of these images, it's a little bit hard to actually distinguish the effect. We don't know what it looked like without the lensing. Okay, and then a lot of what we're measuring in the data are 2-point correlations. And that's the correlation between the property of one galaxy and the property of a second galaxy. And okay, so some definitions that might be useful here. Tangential shear is the component perpendicular to the line connecting the positions of the galaxies. The cross shear is the component rotated at 45 degrees. Galaxy-galaxy lensing is the term for the 2-point cross correlation between a foreground galaxy lens position and a background galaxy source shear. So actually this example is sort of an example of galaxy-galaxy lensing, although something that has this much of a signal would probably be cluster galaxy lensing. And then this last term, which I've already been using, cosmic shear, that's a shorthand for the lensing by large-scale structure, which is commonly measured as a 2-point autocorrelation of a pair of galaxy shears or shapes. So the measurements are quite complicated by certain things happening. One thing is that the atmosphere can blur the image that we receive. And then the other thing is that you can also get instrumental effects. And of course, if you're in space, you don't have the effect of the atmosphere, but you still have some effect from the detector and the telescope. So something about the optics and then detector effects. And one very important quantity to measure is something called the point spread function. And this is the artificial distortion of the image coming from things like the atmosphere, and again, telescope optics, detector effects. And this can serve to commonly, so from the atmosphere, we think of this PSF as, one of the measures is this thing called seeing, which is a quantity that astronomers measure. And that tells us how blurred out these images appear due to the effects of the atmosphere. And typically that effect is larger than what's coming from the telescope or the detector. And it varies relatively rapidly. So the point spread function due to optics varies slowly with time. And this might be described as a combination of diffraction and aberration. What we do in practice, and then here's an image of an intrinsic star, which you can't even really probably see, but it's in the center of the image. It's really a pinpoint-like point source. And that's the original size of it. But as it goes through the atmosphere and different instrumental effects, you get a convolution where it blurs out. And then what we measure is pixelated. And then the image also contains noise. So in the end, we get something that looks like this picture on the right. And so the way to correct for that is to make a selection of stars in the data. And then you measure the shapes and sizes of the stars with, so there are some very well-used tools like PSFX, and then another newer tool called PIF that we use in the dark energy survey. And basically you can make the mapping from this right-hand image to understand what the effect was in the original point source. And then finally, you run a lot of validation tests. And then the other important aspect of the galaxy shape measurement is what is the algorithm that you're using to actually measure the shape of your galaxy. And I've made some groupings here of different kinds of methods. It's a little bit artificial. Some of these are actually hybrid methods, but very roughly speaking, we have model fitting methods, and this uses a light profile with some sort of well-characterized ellipticity, and you make a fit to the actual measurements of the light profile of the galaxy. The statistical approach can be different. The software used by the kilodegree survey is called LensFit, and this is a model fitting method with a Bayesian likelihood. There's also second moments methods measured in either real or Fourier space, where you're actually measuring the second light moments of the directly on the image of these galaxies. And one example is the HSM method, so for the first letters of the authors. And this is a method used by the Hyperborean Prime Cam survey. And then there, I would say, less common methods that might decompose into some sort of basis functions, and also machine learning methods, which as we grow our machine learning methods will maybe become a little more interesting in the future. For all of these methods, calibration is very important. Some methods do a self-calibration process, but ultimately one of the important things that if you're learning about a new shape measurement method, you should ask, well, how well did your method perform in image simulations? Is the output method compared to the input shape, sorry, the output shape compared to the input shape, is that relatively efficient at recovering the original or the truth? And then to go a little bit into detail for what we use for the dark energy survey, we use a model fitting method, but there's a calibration wrapped around it. And this overall approach is what we call meta-calibration. The idea here is that we apply shears to the image, and maybe let's focus on this infographic on the lower right, made by Neil McCran. We start in the top left with some image of a galaxy. We measure its ellipticity. For meta-calibration, we actually just use a single Gaussian, which is on its own, it's not a great fit or not a good model for a typical galaxy. We deconvolve the PSF, and then you get an image that looks like this. And then you artificially apply shear to it. And usually the value is something like 1%, and that will stretch out the image. you reconvolve the PSF, and then you get this epsilon prime, which is the ellipticity that you measure after applying this artificial shear. And then you can also apply a negative shear. So you can kind of go through this process again. And then you have these two different ellipticities that are measured for different applied shears. And so then what you're looking at is the difference in the ellipticities with respect to the difference in the shears that you applied. And this tells you about the response of that galaxy image to the applied shear. And then ultimately, you can say that the average shear is equal to the average ellipticity divided by the average response. And then I was saying that calibration is very important. So if we look at this equation in the top right, the measured shear is equal to the true shear by two factors. There's this M, which is a multiplicative bias, and then there's a C term here, which is an additive term. You can get values of M greater than 0 from things like errors in your model, from noise in the images, blended galaxies, some problem with your PSF modeling, like the size of it. And then you can get additive errors from misestimation of the PSF ellipticity, or some issue with how it varies across the sky. And the idea is that you want to use image simulations where you know the truth. So you have a known gamma true, and then you take your algorithm and make this measurement for gamma measured. And then you can do a fit, kind of like in this plot here, where the ideal has C equal to 0 and M is as small as possible, hopefully 0. And then figure out what are your actual biases. And these two images on the lower left show, this is an example from the DES image simulations paper that came out just maybe a month ago on arXiv. And the left panel is a snapshot of the real data, and then the right panel is the simulated image. And the idea is that you want to get the properties to match as well as possible. So distributions of color, galaxy size and shape, and signal to noise. And then you can say that the image sims are as representative as possible of the real universe, and so that you can build these measurements to understand what these biases are. All right, so now I'd like to talk about how we do the theory modeling and what is the actual connection between the measurements that we make of this cosmic shear to the underlying theory, so the dark matter, dark energy side of things. So again, cosmic shear is, we're gonna refer to it as the correlations between pairs of shapes. And then there's some angular separation on the sky, which here is theta. And we commonly measure these two quantities, psi plus and psi minus, which are telling us about how aligned these galaxy pairs are. So psi plus is a combination of, so I've kind of switched notation here. This plus is the same as what I was calling tangential shear before, and this cross is the 45-degree rotated version. So these are combinations, either adding the correlation of tangential shears and cross shears, or subtracting the cross shear correlations from the tangential shears. And together, this psi plus and psi minus contain information about the underlying matter power spectrum. So psi plus is related to something called the convergence power spectrum through here. And this convergence power spectrum is in turn related to some function Q, which tells us about the properties of the survey. So something about the window function, or there's some important cosmology variables in here, like omega matter and H naught. And then this term here is telling us about the depth of the survey. So what is the redshift distribution to the lenses and the sources and that, so on and so forth. And the other term here is P sub delta, which is the matter power spectrum. And this is where the underlying physics comes in. So the two observables are, this is related to the redshift distributions, and then this is the correlation of the galaxy shapes as defined here. These are what we actually observe in our survey. And then the physics comes into this P sub delta term. And so we make a model of the observables starting with the underlying matter power spectrum, and then we try to match those up. And it's probably useful to note that omega matter and this thing called sigma 8 are the two quantities that lensing this cosmic shear is most sensitive to. So omega matter is the matter density, as you all know, and then sigma 8 is the normalization of the power spectrum on H inverse megaparsec scales. And oftentimes in the literature, you'll see people use a quantity of capital S8, which is a combination of this sigma 8 and omega matter. And there's also two other large-scale structure correlations. I know many of you here work on the galaxy clustering. So this is the correlation between positions of galaxies. And then there's also something I mentioned before, which is the correlation between foreground positions and then the background shape. And that's known as galaxy-galaxy lensing. And these two quantities are very similarly similar to the cosmic shear related to the underlying matter power spectrum. But there are some different factors that are entering into these two types of correlations. So one is the different Bessel functions. So there's a different filtering in the integral. And then the other important thing is that anytime that you're correlating with a position and not with the actual mass, total mass structure, you get a quantity called galaxy bias, which tells you about how biased that position is relative to the underlying matter. All right, so going into some history, now that it's 2021, it's actually been 21 years since the first detections of cosmic shear. But that happened in 2000. There were 4 papers that went on the archive and were submitted to journals in the year 2000. And these are known as the 4 joint detections of cosmic shear. Although you actually see, so this is x-axis is the date, and then y-axis is 90-day read count, which is just one of the quantities you can get from the astronomical data system, like doing a search. I think what I did was a search for cosmic shear appearing in the abstract. And here you see that there are only 3 bubbles. I think one of the papers was on archive but never ended up getting accepted, but it still has quite a lot of citations, but I think I required that it be accepted in the journal. And then more recently, we've been starting to get these results from the kilodegree survey, the dark energy survey, and then the hypersuprime survey is in here somewhere too. And then last year, there's a newer iteration of the kids data that's come out, so that's not shown in this plot, but that's the most recent results. We can also look at this in a more simplified view. So there's the first detections of cosmic shear, and then there are several surveys, the Deep Lens survey, and then the Canada, France, Hawaii telescope lensing survey, both of which I've worked on some aspects of. So the DLS I worked on for my PhD. And currently we're in this period where there are these 3 deep and wide surveys, HSC, DES, and KIDS, that are complementary in different aspects. And then they're all investigating the same omega matter and sigma 8. And then looking forward, we have upcoming the Vera C. Rubin Observatory, And that will have a 10-year survey called the Legacy Survey of Space and Time, so LSST for short. And then also the Euclid Space Mission, I should say, so Rubin is a ground-based observatory. Euclid and the Nancy G. Roman Space Telescope are space-based observatories. And then the timelines might get shifted here by a little bit due to the pandemic. And then as we go to the right on this axis, the size of the teams have really increased, while the statistical error on the quantity we're trying to measure has decreased. Just a quick look, I think I'm running short on time now. A quick look at what the results look like today for cosmic shear. This is the most recent results from the kids degree, the kids survey, the kilodegree survey. And this is a paper by Marika Asghari et al. And we have omega matter on the x-axis and S8 on the y-axis. Again, this encapsulates both the sigma 8, which is like the clumpiness of the structures, and the total matter density, omega m. Kids uses 3 different ways of measuring. There are 3 estimators. The what I described before, the psi plus psi minus, is encapsulated by this 2 PCFs, so 2-point correlation functions. And then there are 2 other estimators, which I won't have time to describe in detail, but they're all complementary. So some are looking at the Fourier space information. And overlaid here is the Planck CMB constraints. And you can see both here and then on the one-dimensional marginalized parameters that the Planck constraints seem to be offset from what both kids is finding and what all previous lensing surveys have found. So I would say that these lensing surveys, so also DSY1 and HSCY1 are included here, these 2 data points. These are all in agreement. DS seems to be a little bit more in agreement with the CMB, but in general, there does seem to be some sort of offset here. And this is at the level of, it depends on how you measure it, but something like 2.5 to 3 sigma. Now, if you combine cosmic shear with 2 other 2-point correlations, so like the galaxy-galaxy lensing and galaxy clustering, and I might point out that for kids, it's done a little bit differently than for DES. So there's some nuances here, but in general, again, looking at omega matter and now looking at sigma 8, so not the capital S8, but sigma 8 on the y-axis, there's still some sort of difference between the results coming out of kids. And then the DES result is this yellow contour here, and then the Planck result in gray. So that's really interesting, potentially, depending on whether you're excited by 2 to 3 sigma. And the question is there something going on between the very early times of the universe when the CMB photons were emitted to where we're making these measurements, where the universe was maybe half its age? So is there some new physics that we're not accounting for, or is there some issue with the measurements, like some sort of systematic that we haven't realized yet? So I'll very quickly just show this image, which is kind of a big flowchart of how we start with images, and then some of this I've talked about today. So the point spread function modeling, shape measurements of galaxies, and how we do the calibration. What I didn't talk about at all, but is very important, is how you do the calibration of the distances to the lenses and to the sources. And then I did also talk a bit about correlation functions. So that's the statistic that we're using for the dark energy survey. And then there's a lot of different tests that we run on the model choices. And we also, importantly, need to accurately measure covariance between these different measurements that we're making. But then in the end, what we get is a likelihood, and we try to make some sort of constraint on the cosmological parameters. I'm going to, again, just very quickly put up this list of systematics worries that we might be concerned about. Two things that we might have some impact from that we have to be careful about how we treat is the impact of baryonic physics. And also earlier I mentioned that sometimes galaxies can be intrinsically aligned due to local gravitational tidal fields. And so that has to be taken into account in the model. So these are roughly grouped into astrophysical, like a category of astrophysical types of effects, and then the middle or maybe more analysis effects, and then the last ones are instrumental and calibration effects. And so these are mostly things like happening in your detector, for example. All right, so just very quickly, there's some results coming out now, just over the past several months from the dark energy survey. Perhaps a lot of you here are familiar with it since it's a large group. And this is a map of the different coverage of the footprint from the original science verification data, which is in red, and then going to the year 1 data. So this has already been finished and released. So that's in green, and it was about 1/3 of the area of the full survey. And then now what we're analyzing is the year 3 results, and that's covering the full footprint, but only to 50% of the full depth. And we've recently released some papers. So the paper that describes the shape measurements for over 100 million galaxies in this Y3 data set is in Gatti Sheldon et al. 2020. And then there's two other really important, there's several important papers, but specific to the shape measurement, there are these 2 other papers, including the PSF modeling, so that's Jarvis et al. 2020, and also McCran et al. 2020. And there are many more to come. So the actual results have not yet, the cosmology constraints have not been released. So there's 2 important takeaways, and I won't talk too much about these figures, except that they're indicating how accurate some of the measurements are and how well calibrated they are. This plot is something called the row statistics. And these are different combinations of correlations of star shapes and sizes. And so I won't define them, but the important bit is that 10% of the signal, cosmological signal, is shown in gray. And these are mostly additive effects to the cosmic shear signal. So basically, the higher the amplitude for each of these panels, the worse it is for the measurement, or the more biased the measurement is. And what's shown here is a comparison between the PSF model results for DSY1 versus Y3. And in all of these cases, you can see that the Y1 measurement was higher. So again, higher is bad. And that enters as an additive impact on the cosmic shear measurement. And we can see in some of these cases, the Y3 version is much more accurate. So the amplitude is much, much smaller. So that's a really good sign. And then there's this calibration from image simulations where in McCran et al. 2020, we measured the mean multiplicative bias on the shape measurements. And we found, importantly, that blending impacts both the shape measurements and the redshift distributions. And this needs to be taken into account. And that's something that we're going to include in the modeling of the cosmology constraints. And just quickly, these are for the 4 tomographic bins, so bins of redshift, for which we're measuring the shear correlation functions. It's the multiplicative bias on the x-axis, and then there are different methods of treatment for the redshift distributions. And because this is a very new approach, we're not quite certain which of these are the best method for doing the treatment of the redshifts. And so the idea is that we're doing several of them to get an idea of what is the systematic error, like how different can they be? And that gives you an indication of what is the systematic error based on your modeling of and choices made in the analysis. And the final results are the bottom row here. All right, so I don't have time really to talk about the Roman Space Telescope, but it's going to be really exciting. The launch is in 2025. And it's about 100 times the field of view of Hubble. And this is a figure showing the 18 near-infrared detectors on the focal plane. And it's really going to be, it's a total of 0.28 square degrees in the sky. So we're going to be able to image a lot more than, for example, Hubble in a relatively short period of time. And then Roman is very complementary with both LSST and Euclid. They're covering different parts of the wavelength range, and then they also have different depths. So I think taken together, these are going to be very complementary. And this is a plot taken from a paper by Tim Eifler showing two dark energy equation of state parameters and then the constraints that we can get from, so it used to be, Roman used to be known as W first, so the survey done first, and then also in combination with LSST. So the combination is the smallest contours here. There are actually lots and lots of other interesting measurements that we can make and combine from these different experiments. I've really only talked about cosmic shear. So some of what we're talking about now has to do with survey strategies for how to best synergize these different experiments. And the final point I'd like to make is that now we have these really huge teams. So another thing that many of us are thinking about are how to be equitable and good at communication and inclusivity in these large collaborations. Okay, so I'll just end it here, just a summary slide. We're eagerly awaiting the final results of DS and where it falls exactly on this plot as we are nearing percent level precision measurements. So thanks very much, and I'll take questions.
Okay, thanks very much, Ami, for this very broad overview. It was really amazing. You could cram all this content into a talk, even though, as you said, you had to leave out a few items, which actually might raise a few questions, at least on my side. But first of all, I'd like to open the floor for questions. Just please speak up if anyone wants to, anyone wants to ask. Okay, let me see if there's any raised hands. Okay, so in the meantime, just to flex those question muscles. You were, one thing that you had to just gloss over is the systematics question. Could you explain, well, what are the most worrisome of those in the forthcoming years? I mean, is anyone going to be, a substantial floor for any further statistical improvements?
I think before DESY3, we would have said the photo-Z errors were one of the dominant errors. But actually, if you look at the papers that have already come out for some of these calibrations of the N of Z, so the redshift distributions, the methods actually seem to be pretty, like the systematic error seems to not be as big of a contributor as we thought it might be. Mm-hmm. Although we're still learning quite a lot about the method, so that it will still be very important. In contrast, I would say that blending is, we knew that it would start to be a problem, but now actually we realize that blending affects, well, both the galaxy shapes and the redshifts. So I guess, yeah, so that means redshifts are still important, but in kind of a different way than what we had originally thought. And this will become worse for the full DES dataset because the full DES dataset reaches much deeper levels, and then also LSST is going to be very, very deep. And so you're going to have a lot of galaxies that are blended together. So I think from the measurement side, blending is maybe going to be a big contributor that we have to figure out how to address. And then these two are, from what I understand, the most important modeling or the astrophysical uncertainties. For, I would say this intrinsic alignments in particular is a problem because there's not really any fiducial model that's used by all of the surveys. They use different, probably wrong models to describe the intrinsic alignments. So for example, KIDS uses this nonlinear alignment model. And then DES uses this tidal alignment, tidal torquing model, which has more parameters. And so it kind of blows up the error bars a little bit, but then there's certain aspects that may or may not be matched to data. So maybe the key is to learn a lot, make more direct measurements of the intrinsic alignments, which maybe some people on the in the audience might be involved in, since combinations with surveys like POW, that's going to tell us a lot about the intrinsic alignments. But yeah, we kind of need these surveys that have good spectroscopic information or really great photometric information, and then also something about the shapes of the galaxies, so you can actually measure the signal, the intrinsic alignment signal. Yeah, I think maybe these top four are probably the main quantities that like all surveys will have to deal with. And for some of this space-based one, this slide is a little bit biased toward Roman in the sense that a lot of these uncertainties are more impactful for the Roman Space Telescope and probably Euclid as well, as opposed to LSST.
Okay, any questions from the audience?
Hello, perhaps I have questions.
Yes, go ahead, Roderick.
Okay. You told us, thank you for the nice presentation. It was very useful. So you said there is a slight excitement about the difference between Planck data and the other experiments about this SH. I wanted to know if it's correlated with the Hubble constant, because in your formula I saw that the Hubble constant is there too. So is this related, or is this disentangled? Because there is a tension also in H0, as you know, about the Hubble telescope, which Hubble constant, which there is a tension to. If it's related or not is my question.
Yeah, that's a very open question. I think that there is some possibility that it is related, but so far we haven't found any direct connection. The lensing information, so lensing, you saw earlier in some of the equations, H0 does appear, but actually if you look at the likelihood surface for constraints on H0, coming from lensing is very, very mild. Like there's not much information that lensing gives on H0. So yeah, lots of degeneracies there. I have heard there are models like early dark energy, which people have proposed to help address the H0 tension, which then other people have looked into whether that makes this tension better or worse. And I've heard actually that it doesn't actually, so solving that H0 tension with early dark energy doesn't necessarily make this better. So it's certainly an area where people are looking into different theories, but from what I understand currently, there's not really any very compelling physical model that solves both of the tensions. So I would say it's possible that they're related, but it's not anything that's obvious yet.
Okay. Any more questions? All right. So yeah, I think that was a great overview. Thanks again, Ami, for the talk. As you all know, we have the agenda that was linked in the email. You can look at the talk. Eventually, the presentation itself, the video will be posted as well, so you can have access to that. And thank you all for coming, and see you soon in the Ethernet. Bye-bye.
Yeah.